Okay, so I have just got the lab posted up. Sorry, I forgot about that Wednesday, but it's there waiting on you now. Can't wait to see that. So the lab that we're going to be doing this week is the EDA lab, or EDTA, ethylene diamine tetracetic acid. It's a titration, but it's for metal analysis, so it's a little bit different than the acid-based stuff that we've been doing so far this year. This will be our 6th lab experiment, and we'll just do 10 for the year, so we're more than halfway done with the lab. So painful lab reports that you have to write, you're over the hump there, I'll tell you that. So, all right, we're going to finish up the chapter today, and I'm going to show you a couple of specific examples of doing systems of equations. We're going to do some where we solve them completely, and we do some of them where we're going to use approximations, and then we're going to do some that we plug into Mathematica. So I should say these problems take a little bit to do. So we may not get through the 3 or 4 problems in the hour. If we're not, we'll finish them up on Wednesday. So one of the ways that involved a constant calculation becomes a little bit more dependent upon the environment are metal hydroxides. So metal hydroxides associate to the metal cation and the hydroxides. And the key thing is that these solubilities are directly pH independent. If you change the pH, you change the OH minus concentration, therefore you alter that. Now we can control it a little bit if we do this in a buffer. A buffer by definition is a solution that has a controlled pH. We can fix pH, therefore the OH minus is known. It becomes a common ion effect problem. So this is a common ion effect if pH is buffered. And that makes life simple, but when it's not buffered is when it becomes complex, because pH is a function of solubility. So I'm going to work a couple of these, and let's look at this guy first. So this one is the magnesium hydroxide solubility. So magnesium hydroxide dissociates into the magnesium 2+ cation and 2 OH minuses. And I can write a KSP expression for that. KSP equals the concentration of the magnesium, 2+, up there, times the concentration of the hydroxide ion minus squared. And that's coupled because it's in water with the autopolysis of water. So water associates to the hydronium ion, or the H+, and the hydroxide. That equilibrium is described by Kw. So we've got that handled. Now if I look at the number of unknowns that I need in this equation, I've got 1, 2, 3 unknowns. I need 3 equations. So I'm short 1 equation. And for metal hydroxides, the charge balance and mass balance equation are the same. So it kind of makes life easy for us if we recognize that. And the easiest one of those to write, certainly, always is the charge balance equation, I think. So our charge balance equation, you put the autopolysis of water in, and you just simply add the things that are positive and negatively charged. There's only one of the species here. So this becomes the 3rd equation that we do in the system. 1, 2, 3 equations. So at that point, I've got a mathematical solution. I've got 3 equations, 3 unknowns. We can solve that mathematically. What I want to try to do is to see if I can come up with a solution for it. So one of the things that I can simplify is I can work in simplifying or reducing equation 3 down. So I want to see if I can do that a little bit. So I'm going to say from 3. In equation 3, the reason I can simplify it to 2, is that it has addition and subtraction, or subtraction. And the thing I could either say is either the H plus is much, much greater than 2 times the magnesium concentration, or the opposite way I could say it is that maybe 2 times the magnesium concentration is much, much greater than H plus. Well, I know if it's just water, the H plus would be at 1 times 10 to the minus 7. And magnesium concentration, since this is a 1 to 2 salt, I'm going to be taking the cube root of KSP if I was just finding the solubility. So I think this would probably be, magnesium be somewhere like 10 to the minus 4th. So in my mind, I think this is probably the most predominant term. So I'm going to make the assumption, and this is where you get in trouble if you don't check it and you're wrong. I'm going to assume that it is this conditions. So 2 times the magnesium is much, much greater than the H plus. So this term becomes insignificant and drops out of the equation. So it says that 2 times the magnesium is equal to the OH minus. Okay, now if that's the case, if I'm looking for pH in this, so I need to find what is OH minus in this guy. So I can take and arrange this equation in whatever way I want to find out what a solution is. Okay, so if I look at putting this into 2 times the magnesium equal to the hydroxide, I can substitute that into equation number 1. All right, so if I'm going to go up to substituting that in, so if I know that 2 times the magnesium equals the hydroxide, that means the magnesium is equal to the hydroxide divided by 2. So what I'm going to do is take this term and substitute into the KSP expressions. Now I can solve for the hydroxide. So I've got the hydroxide, or KSP, is equal to magnesium, which is the hydroxide divided by 2, times the hydroxide minus squared. So now I'm going to multiply the 2 over, so 2 times KSP equals the hydroxide cubed. So now again, you get rid of the cube, I need to take the cube root of both sides. Cube root. That says the hydroxide minus is equal to the cube root of KSP, which is 7.1 times 10 to the minus 12 times 2. All right, so let me find out what that value is. How do I get the what now? Cube root of 2. Okay, I took on this equation, I took the 2, multiplied this side, hydroxide, and times hydroxide squared. Gives you hydroxide cubed. If I did my math right, I got 2.42 times 10 to the minus 4th molar. Okay, so now I need to go back, and before I solve for what pH of that is, I need to see, was my approximation valid? So this is the method of approximations. So I need to ask the question, was what I tried valid or not? Okay, so I said that 2 times the magnesium was much, much greater than H plus. That's what I did to simplify this equation. Well, I know that the relationship between the magnesium and the hydroxide, if this was S, this was S, this is 2S, that the magnesium is equal to 1/2 of the hydroxide concentration. So the magnesium concentration, which we said was 2.4 times 10 to the minus fourth, it's going to be around 1.2 times 10 to the minus fourth. And we need to compare that to the H plus. Well, what is the H plus? Well, the H plus, if I know that hydroxide is 2.42 times 10 to the fourth minus fourth, I can solve the KW expression. Find out what the hydroxide is. And it's 4.2 times 10 to the minus 11th. So 4.2 times 10 to the minus 11th. So now I can check and see is it valid or not. So I've got something to the minus fourth power. Is that much greater than something that's 10 to the minus 11th, 7 orders of magnitude? So that means validated. Okay. So now I can go back and find out what is pH of this. I know what POH or H plus is, so I just take the negative log. pH of that guy is 10.38 if I go 2 sig figs. And I have 2 sig figs here. Okay. At this point, I could have solved it with Mathematica. I'm going to teach you that in the chapter. But on this one, I could make an approximation that made just simple substitution with algebra. Okay? All right. Now, it doesn't always work that well. And sometimes it works easier. So let's do this one. So here I want to do what's the solubility of a saturated solution of magnesium hydroxide. And now I've got it buffered at pH 10. So now I'm not looking for pH. Now I'm wanting to know what is the solubility of it. Same dissociation. What makes this one different? I got the same KSP value. Nope. All right. I don't know which one's correct. Yeah, this is all right. Should be that 7.1 times 10 to the minus 12. Okay. So it's the same system, but now if I look at the autopolysis of water, this one is unknown in the system because the OH minus is going to be something that's a known value. I know it because pH is given. If pH is 10, that means POH is 4, which means the OH minus is 1 times 10 to the minus 4th molar. So now solving it is just taking the KSP and doing a common ion effect problem. Okay, so if I'm looking for the solubility is equal to the concentration of the Mag2 plus. So the concentration of the Mag2 plus equals solubility is equal to KSP divided by the hydroxide ion minus squared. KSP is 7.1 times 10 to the minus 12. The hydroxide we said was 1.0 times 10 to the minus 4th. Got to remember to square it. So that's going to be 10 to the minus 8th. So 7.1 times 10 to the minus 4th molar, if I can do math right in my head. Okay. Now this one, there's no approximations or anything. The thing that makes this problem simple to solve is the fact that it's buffered. The fact that it's buffered, take both of these things out as variables. I know their concentrations. And that makes life easy for me because if I know the H plus, I know the OH minus, I know the OH minus from the equation below, therefore it eliminates one of the unknowns. The only unknown I have in this system is the concentration of magnesium. So I just need to solve KSP for the magnesium using the common ion effect. Okay, so a problem like this, you look for the word buffered, and that's a happy face problem. That's the one I'd expect all of y'all to be able to get that type of problem. If it's one where its pH is controlled by, like on this one, that we could have solved for any of the three variables. We could have went after the solubility, pH, or what is the OH minus. But you still had to do the same system of equations to solve any of the three. This guy, it is really straightforward. Okay, so let's look at this guy. So here's another one of the solubility ones. This one has a much lower solubility associated with it. Iron 3 hydroxide. Dissociates in the iron 3 cation. Oops. That. Plus 3 hydroxides. I can write a KSP expression for it. The concentration of the iron 3 down to the concentration of the hydroxide minus cube. And its KSP is a very low 1.0 times 10 to the minus 36. Now that's the reason we like scientific notation. You don't want to write out 36 spacing zeros. Alright, so I've got a KW expression. KW equals H plus times OH minus. Alright, and we know its value is 1.0 times 10 to the minus 14. Okay, so the number of unknowns that I have in this are 1, 2, 3. I've got 1, 2. I need a third equation. That third equation is going to be my charge balance, which equals the mass balance equation. This is still a metal hydroxide. So metal hydroxides, mass balance equals the charge balance. So that's going to be 3 times the concentration of the iron 3 plus the H plus yields the OH minus. Okay, now if I think about this one, it dissociates as a 1 to 4 salt, or a 1 to 3 salt. And if you remember the equation, if it was a 1 to 3, it's something to the 4th root of KSP to solve solubility. Okay, so it's, I don't remember the, you'd have to take 2 to the, and we'll develop the equation for it in a second. But it's going to be a 4th root of it. And a 4th root of this guy is still 10 to the minus 9th. And the fact that that's 10 to the minus 9th, this one may be close. I'm going to think this guy's probably pretty low. But I know from the autopropylasis of water that H plus should be there around 10 to the minus 7. So on this one, I'm going to guess the other way. And if you're not sure, you take a guess. And you try it when you check your approximation. I'm going to assume that the H plus is greater than the 3 times the concentration of the iron.
But you get to the minus 9, you took the 4th root.
I just took the 4th root of it as approximation. Okay, so if that's the case, what happens is that this term becomes insignificant and drops out. So this reduces to H plus equals OH minus. And that only happens at one time. I could plug that into KSP and solve that, but I expect it. That's pH 7 at 1 times 10 to the minus 7. All right, so now I'm going to check that and see if that's a valid thing to have done. All right, so because that at that point that's solving my unknowns for me. So if I look at the relationship, if this was solubility, this was solubility, this was 3 times solubility, I need a relationship between the iron and the OH minus. So if I look at it, the iron times 3 is equal to the OH minus concentration. Okay, so the OH minus, we just said it from our approximation, is equal to, well, I want to know the iron, so that's correct. So I need to divide it by 3. Let me not confuse you here. Let me take this stepwise. Leave that there. I don't want to take shortcuts y'all don't see. Okay, so this is from the statement above. It's 3 times the hydroxide's 3 times the iron. Okay, so that means the iron is 1/3 of the hydroxide. So that yields that the iron concentration is equal to 1/3 of the hydroxide concentration. Okay, so we know the hydroxide is 1 times 10 to the minus 7th. Okay, divided by 3. So that's going to be 3.33 times 10 to the minus 8 molar. Okay. Now, if I know that term, I can compare it to the H plus. So the H plus concentration was also 10 to the minus 7th. So 3 times the iron here. If I go back in to check the validity of this, I want to know is 3 times the iron concentration greater than, significantly greater than H plus. All right, so it's at 3.33 times 10 to the minus 8. So 3 times 3.33 times 10 to the minus 8. All right, and this guy is 1 times 10 to the minus 7th. And I find out it's not going to be true. Because multiply that out, you're back at 1 times 10 to the minus 7th. This is not valid, not true. So the assumption that I made here turns out to be false. So this assumption is not true. So how do we have to solve that system then? The fact that the two things come out practically equal to each other, this is one of the ones, even if I turn the inequality around the other way, neither term is significantly greater than the other term, and you're going to run into problems like this. Not that often, but sometimes you will. This is the frustration to me in using the method of approximations. Sometimes it just doesn't work. All right, so that's what I want to teach you. There's a better way. So this is kind of my segue into that problem. All right, so here's our better way in life, in my opinion, and that is to use Mathematica. So you can download it or you can use it on one of the many computers on campus. But find a computer that's got Wolfram Mathematica on it and then launch Wolfram Mathematica. Try to blow it up big enough that y'all can see it.
On our test, you're just going to have us do approximation.
I'll either, well, we're going to do some, we're going to do with the exact solution you'll see in a minute. So we're going to do some, you can solve these without It's not always fun, but you can. New document. All right, I want to get these get this large enough that you can go back and review this if you need. So the function in Mathematica we're going to use is called the nsolve function. So I'm going to go nsolve, capital N, capital S. All right. I want to make it so you have to go back and then review this, and we'll try to make it even bigger than that. And then the way that it works in Mathematica is you define a series of equations, and then you define the variables, and you have it find the solutions for you. Okay, so we're going to go back and do that previous problem that we just hung up on. So you have to go square brackets, and then, in lack of a better name, squirrely brackets. Okay, and then you need to define your equations. Equations have to be separated by a comma, and then they need to have an equals equals in between the terms in the equations. So first thing I'm going to do is go in and put if I look back at my equations I have. So my three equations were KSP. I'm going to put that one in first. So KSP was 1.0 times 10 to the minus 36 power equals, and then Fe times the hydroxide to the third power. All right, so that's my first equation. All right, my second equation is going to be the autopropylus of water. So 1 times 10 to the minus 14th equals H plus times OH, comma. So what it's done is the things that it thinks that are variables, it's made blue for us. All right. So there's one more equation to put in this, was the charge balance equation. 3 times the Fe plus the H plus equals the OH minus. All right. That's the three equations that I have, comma, or squirrely bracket. I'm closing the first one, comma. I'm opening a new one, and the new one is going to define my variables. So my variables are Fe, H plus, OH minus, close the squirrely brackets, and then square brackets to close. And I'm going to hit Shift Enter. And it says, these are what I think the solutions are. All right, so if I look at these numbers, there's a couple of them that have complex numbers in them. It's got I's. And there's some that have negative concentrations. Those are not the real roots. There's only going to be one set of solutions that have real roots in it. Okay, so now on this one, I look at it, it says that the value for the iron is 0. Now, part of our problem in this is we've got a really tiny number in here. So let's see if we can convince the computer to do otherwise. So I've worked with Dr. Moretti, and I should have probably come up here and tried this on this computer. You can change the precision on these new computers so that it changes the
Did you put any spaces or hit enter at any time?
I hit enter at the end of each line.
Okay, after a comma?
Yes. Yeah. Alright, so let me get the so Dr. Moretti wrote this line of code that we could copy in there that just gives you your positive roots and it throws everything else away. That's not the one I'm looking for. Okay, here's the one I'm looking for. So usually the default is to carry a calculation out to 20 decimal places. I would like to go further. Okay, so I would like to go to more decimal places. So I'm going to tell it to take it out to 100 decimal places in the calculation. Because here we're running with such small numbers, I think that may be what we're running into. And solve. So I'm just going to copy that and put that below that line and try to solve it again. And it's still the same problem. All right. That is my frustration with this. Okay. Now we have a set of solutions. So, get this one up higher. And I will copy this this line of code of machine unprotect, all positive ends apply to that region of the interval from 0 to infinity. This is the code that you have to get to keep the computer from doing rounding on you. Okay, so now when I did it, I apply my solutions to it. It kicks out the 4 roots to it, right? And it gives me a concentration of the iron is 1 times 10 to the minus 15th, the H plus is 1 times 10 to the minus 7th, and the OH minus is 1 times 10 to the minus 7th. Okay, so these top 2 up here have complex numbers in them. Which one of these bottom 2 is it? Is it the third one down or fourth one down? Why the third one? OH is negative on the last one. The one that's going to be the real root is the one that has all positive concentrations. Okay, so that's the beauty of using mathematics on this.
Were we right? We assumed that.
That those 2 terms were correct. Yes, but we couldn't make the simplification to solve with the iron concentration. That was our problem. Yep. So either way you would have went, you were going to run into problems. Okay, so let's tell you what. Let's do a different clicker question today. We'll come back to that. Okay, we're going to do that one because I want to work some more problems quickly. Okay, so all right, no C is an answer. All right, let's go back and look at where life becomes more complex. So that's what we like, is life gets complex. These used to be called complex equilibria. Now the book changed the definitions in the chapter. Whenever we perform analytical precipitations, we always do them in buffers for the reason we just saw with the metal hydroxides. Life gets rough if we don't use a buffer with it. And the reason why we want to do that is that takes 2 unknowns out of the system. I know what H plus is, and I know what OH minus is. I can solve for both of those concentrations. Okay, so I want to do an example is what is the solubility of barium carbonate at pH 7? And what makes this a complex system is that it's not just the solubility of the barium carbonate, it's also that the carbonate ion is a diprotic acid coupled with carbonic acid. So this one's got some steps involved in it. All right, so we're going to see if we can come up with a solution mathematically, and then we may look at the other way of doing it. So I'm going to write out my my expressions. So barium carbonate dissociates. I know there's only one of them. Don't need any parentheses there. Barium carbonate solid dissociates to form the barium cation 2+ and a carbonate. And I can write a KSP expression for that. It's equal to the concentration of the barium 2+ times the concentration of the carbonate. All right. Carbonic acid dissociates to form H+ and bicarbonate. I can write a K1 expression for that, products over reactants. Right. Now the one that's coupled to our equilibrium is the bicarbonate dissociates to form H+ in the carbonate. But the key thing is every one of those is tied together. So I can write a Ka2 expression for it. So it would be products over reactants. Okay. Could I write a Kw expression? It's buffered. So if I did a Kw expression, they're knowns. So there's no advantage to me to do that. I know H+ and I know OH- because I know pH in this system. So if I look at the number of unknowns I have, we remember our strategy was to come up with the number of equations at least equal to the number of unknowns. I've got 1, 2, 3, 4 unknowns. Right? But I already have 1, 2, 3 equations. Right, so here's another important trick, and I'm going to write this in red, and I'm going to make it big. If there's a buffer, there's no charge balance equation. The problem is I don't know what all ions are in that buffer that are contributing to control pH. So there's no charge balance equation that I can write on this. So that tells me the next thing I've got to come up with then is a mass balance equation for it. So equation number 4 is going to be a mass balance equation. So if I look at my mass balance equation, if I'm just looking at the solubility of this thing, I know that the barium concentration, which barium's only in one form, has to equal the total carbonate concentrations. But the carbonate can be in several forms. The carbonate can be in the form of the free carbonate, as it dissociates into, or it can pick up a proton and be in the form of bicarbonate, or it can pick up a second proton and be in the form of carbonic acid. All right, now I have 4 equations, 4 unknowns. I have a mathematical solution. Now I know that you look at that and you think, well, solve that with algebra, you're crazy. I want to show you it's not that bad. I guess that's a relative term. All right, so the strategy that you're going to use for this one is to solve mass balance equations in terms of carbonate. All right, so I want to take both of these terms out of the K expressions, the Ka expressions, and try to express them in terms of carbonate. And I'll show you why there. So first thing I'm going to do is take equation number 1, or number 3. So I'm going to put from 3. So equation number 3, this guy. And I'm going to rearrange that to say that the bicarbonate ion is equal to the H plus times the carbonate divided by Ka2. So all I did was took this term, put it up here, put the Ka2 down the bottom in the rearrangement. Okay, and the reason I did that is because I know H plus and I know Ka2. pH is given, so I can calculate H plus. Ka2 is given to me in this table. I can express the bicarbonate in terms of carbonate. And I get that it's a fairly large number. It's 2,132 times the carbonate concentration. All right, I'm going to do a similar calculation with equation 2. From number 2, the carbonic acid is equal to the H plus. Okay, I'm going to change the colors here so those two don't run into each other. Sorry. I'm going to be writing the same thing. It's just go back to black. The carbonic acid is equal to, I'm going to take this equation and rearrange it. I'm going to put this term on top, this term down on bottom. So it's equal to H plus times the bicarbonate divided by K2.
Wait, wouldn't it be?
K1, thank you. K1. So now I know H plus, I know K1, and I found out what the bicarbonate was in terms of K2, so I'm just doing the double substitution here. So 1 times 10 to the minus 7th is H plus. For the bicarbonate, I'm putting 2,132 times the carbonate, and K1 is 4.45 times 10 to the minus 7th. Right. 1e to the 7th minus times 2032 divided by 4.45. Right, and I got 479 times carbonate. Anybody else get that? Okay. So now what I'm going to do is I'm going to extend the page down a little bit, and I'm going to plug these into the mass balance equation. When I say these, both of these are just solved for. So now the concentration of the barium is equal to the carbonate plus, for bicarbonate, I know the bicarbonate is equal to 2,132 times the carbonate. And for the carbonic acid, it's equal to 479 times the carbonate. All right, so I can add all those together. So I've got 1 plus 2132 plus 479, 2612 times the carbonate is equal to the barium concentration. All right, so now I can take this, go back to the KSP expression. So into equation number 1, which is our KSP expression, that says that if I'm looking for, it's easy to forget what you're looking for. I'm looking for solubility. I'm going to solve it in terms of barium, because that's the only thing that doesn't change on this. You wouldn't want to solve it in terms of carbonate, because carbonate fluctuates with this one. So now plugging this back into 1, I can say that the barium concentration which equals the solubility is equal to the KSP divided by the concentration of the carbonate. No, it's not a common ion effect. Let's not say that. Let's go back to our KSP expression. So what I'm going to do is say that the carbonate ion in terms of the barium. It's not a pin. We're going to finish this problem. Carbonate ion is equal to the barium. Okay, what I'm going to do is divide the 2612 to the bottom. Okay, now I can substitute that into KSP. KSP is equal to the concentration of the barium times the concentration of the barium divided by the 2612 for the carbonate. That says that barium squared is equal to 2612 times KSP. So now I'm going to need to get rid of the squared. It says that barium is equal to the square root of 2612 times KSP, and KSP was way back here, forgotten, 5 times 10 to the minus 9. Be a positive 9. And I got 3.6 times 10 to the minus third. And that equals the solubility, yes. No approximations, no solutions, just a little algebra. Or no solutions, no simplifications. That's just an algebra problem. It's a long algebra problem, right? Would I expect you to do that? It's been a bonus question before. So the key thing is just think about the strategy. Now, we're out of time today, but I'm going to show you. So we spent a solid 15 minutes doing that problem. I want to solve this same problem, finish it up on Monday on Mathematica, and I want to show you how long it takes us to solve the same problem in Mathematica. So it's going to be less than 5 minutes. And then we're going to do some more solutions in Mathematica. I'll have Chapter 9 notes loaded. Your lab is loaded for today, so I got that printed out right before it came to lab, or it went online right before we came to lab. So we'll get a copy of that, and I'll see you at 1:15.
Oh, good, because I wasn't going to I had to take a quiz.
Oh, you can.
And I need to look over the book before I forget. We can 11.
Yeah. the